Dear students, welcome to the solution analysis for your homework 4 of wireless communications. So this homework had three problems, I guess, one, two, three, yes. And the first problem, question 1, it contained 50 points and the next two contained 25 each. So let me go through the solution of them. So in the first problem, you were given the H matrix or the channel matrix of a 2 cross 2 MIMO system, and the singular value decompositions were also given, but some of the terms were kept unknown here. So the eigenvalues of the H matrix are, lambda 1, lambda 2, and then this is x, this is y, and you were asked to calculate the values x, y, lambda 1 and lambda 2 without using MATLAB. And then you were asked to calculate the capacity of the equivalent MIMO system where both transmitter and receiver knows the channel state information, or in other words, both transmitter and receiver knows all the parameters of your H matrix, and you are asked to calculate the channel capacity given the total transmit power, noise, and the noise N0, and the bandwidth B. And then you are also asked to calculate the capacity of the equivalent CISO channel and comment on the capacity enhancing ability of MIMO. So for the first part, you can do two things. You can just multiply these three matrices, and you will equate each of the elements of the multiplied matrix with the elements of the actual H matrix. In that way, you will have four equations in x, y, lambda 1 and lambda 2, and you have four variables, x, y, lambda 1 and lambda 2, so you can solve the four equations and get the values of x, y, lambda 1 and lambda 2. But then also you can use the property of the decomposed matrices. So this is your U matrix and this is your V matrix. So the eigenvalue decomposition of H is given as UdV. So you can use the properties of the U and V matrices, which are basically unitary matrices. So if you do U Hermitian, or U Hermitian U, you will get an identity matrix of order n, where n is the number of antennas in your receiver, and V, similarly you can do the same thing with V Hermitian, or V Hermitian V equal to IM, which is an identity matrix of order m, where m is the number of transmit antennas. So so this, you can use this very intelligently to just calculate this part. So you can use this matrix, you can multiply this matrix with its transpose. I mean, Hermitian or transpose is the same thing if you have all real variables. If you have complex numbers, then Hermitian is the complex conjugate transpose. But in this case, you have real numbers, so it is just the transpose. So if you multiply this matrix with its transpose, and that will be an unitary matrix. Okay, so in that way, that will be a unitary matrix of order 2. So in that way, you can just find the value of x by doing this. You will have one variable, and you will directly get the value of this variable by using this property. And then similarly for y also, you can use the same property. You can multiply this matrix and have it equated to an unitary matrix and get the value of y. That method is quicker, and some of you have used that. And then once you get x and y, it's easier to manipulate the three matrices and get the value of lambda 1 and lambda 2 using this equation. So most of you found correctly all the values. The final values will be x equal to minus 0.5625, y equal to 0.7318, lambda 1 will be 15.57 and lambda 2 will be 4.07. So once you calculate all these values, and then you can use the equations of the channel capacity using the water filling algorithm, because in this case your transmitter and receiver both knows the channel state information. So you can use this formula to calculate the capacity. So the power allocations on each of the equivalent channels will be based on this water filling algorithm. So you have, you know, the lambda i's, which is lambda 1 and lambda 2 from part A. So you can use this equation, and the total power will be equal to the 20 milliwatts. So this will give you the value of mu, and once you calculate mu, you know lambda 1, lambda 2, you know the bandwidth B, so you can calculate the capacity based on this formula, and then that will be equal to 3.87 megabits per second. And then using the same power, I mean signal power and noise power, you can use the capacity of the equivalent CISO channel, and that will be 1.33 megabits per second. And then you can clearly see that the MIMO enhances the capacity by adding diversity to the system. The next question, you were asked to prove that like if you have the capacity of a MIMO system where only the receiver knows the channel state information, and if you have this condition, let's say, so all the singular values, the sum of all the singular values are bounded by a maximum, then you have to show that this capacity is maximized when you have all the singular values equal. So this type of problems where you are asked to find the maximum of a certain function subject to a constraint, this type of problems can be solved using the theory of Lagrangian multipliers. This is a very common methodology in multivariate calculus, and I'm sure most of you have come through this concept in your high school or early college mathematics classes. So let me review this. So here is the concepts of Lagrangian multiplication and the theory of Lagrangian multipliers basically. So when you have a function, let's say f of x, y, and so on, like there are many variables, and this is a multivariate function, and you are asked to maximize or minimize the function f subject to a constraint that is given by another multivariate function, let's say g. So g is also a function of x, y, and so on, and g is equal to c, or let's say g is less than equal to c, then you can write you can introduce a new variable, and you can write a new function L, which is called the Lagrangian, which is a function of x, y, all the variables plus the new variable lambda, and then you can write it as f of x, y, and all the variables minus the new variable times the constraint. So in this case your constraint is the function g equals to c. So you can write this constant at g minus c and then multiply it with the multiplier lambda, and then you obtain the new function L, and then you minimize that function or maximize that function based on setting the partial derivative or the gradient of that function to 0, and then find the solution of this, and then try to find out the particular solution that gives you the maximum or the minimum that you are looking for, and that particular value of x, y will give you the maximum of the function or the minimum of the function, and the corresponding value of lambda will give you the value of the multiplier. So we are using this concept in solving this problem here. So basically here my constraint is that sum of all the eigenvalues is less than equal to lambda bar. So I am introducing a Lagrangian multiplier mu here, and I'm writing this constraint equation, in the form as the sum of all the eigenvalues minus the maximum value. So this is the new constraint written in this form, multiplied by the Lagrangian multiplier, and this is my original function, so which I want to maximize. So the Lagrangian equation is given by the original function minus the Lagrangian multiplier mu times the constraint written in this form. So now if I take the partial derivative of the Lagrangian function there and set it to 0, this will give me the value of all the lambda i's. So this will gives me the lambda i's in terms of the different parameters of the original function m, sigma square p, and the Lagrangian multiplier mu. So this value of lambda I, you can see that this doesn't depend on I. So this is the same value. This value is a constant because this doesn't depend on I. This is based on all the parameters of the original function, and these are all constants. M, sigma square, p, mu, all are constants. So therefore all singular values have the same value lambda I given by this value. And if you now sum all the lambda i's and set it less than equal to lambda bar, which was the original constraint, then you will get this equation. So your lambda bar is equal to this, and therefore you can calculate mu, which is the Lagrangian multiplier. So mu is given by this equation. So therefore you can show that the capacity is maximized when you have all this value equal to the same value, and that same value is given by this value. So this is the way to solve this type of problems, but many of you have used different inequalities and used the property of those inequalities to solve the problem, but those inequalities most of them didn't use this constraint. So this is important, you have to use this bound. So therefore you lost some marks because of this, because this bound was never used. So you can use the properties of the inequalities, but this bound has to be properly used, and your solution didn't have a proper explanation, so I had to deduct some marks. So this was the solution of problem 2, and in problem 3 again you can write the Snr expression. So this was basically a 2 cross 2 MIMO. So in a 2 cross 2 MIMO you can write the Snr expression like this. In this case you have the parameters of the H matrix given as HI1 and HI2, where your I goes from 1 to 2. So you can write the parameters, I mean, you can write the signal in terms of your gains of the H matrix and like this, and similar to the lecture notes, you can write the expression of your SNR in this form, and using the Cauchy-Schwarz inequality you can show that the upper bound of this expression is this, and this will simplify the above expression and you will get the SNR less than equal to this value, which is basically the trace of your H matrix multiplied with its Hermitian. So this particular expression is same as the trace of this, and then you get for MGC you have this expression, and for EGC you have this expression, because your the 2 term will come in the denominator for EGC, because all the alphas are equal. So if you put the alphas equal here, then this will be these alpha i's will be equal to some value, let's say alpha, just alpha, and if you add this, then this will give you 2 alpha square, and the alpha square terms on the numerator will cancel out and there will be a 2 term here. So that 2 terms comes for the case of EGC, and this one is for MGC. So that's the solution for your problem set 4 for wireless communication. Thank you very much.